Hello viewers, in this session we will see Laurent series expansion of functions in a neighborhood of singularity, particularly poles and essential singularities, and we will also see the Cauchy's residue theorem. Okay, so, firstly to motivate this discussion, let us look at the expansion of 1 by 1 minus z, the Taylor series expansion of 1 by 1 minus z, which is around 0. This is equal to sigma z power n equals 0 through infinity. Okay. And then this is valid for modulus of z strictly less than 1. Okay. And now, after having studied singularities, we know that this power series expression of this analytic function, okay, function analytic at 0 is only valid on a ball of radius, open ball of radius 1, because this function f has a singularity, it has a simple pole at z equals 1. Okay. So, that is the scenario. What is happening is that here is 0, okay, and then the function has a simple pole at z equals 1, okay, simple or not, that is not the point, but it has a pole at 1, and then so the Taylor series expansion around 0, okay, is valid in a ball of radius 1, okay, open ball of radius 1, okay, and that ball can have a maximum radius 1, because at 1 there is a certain resistance, there is a pole. So, the Taylor series expansion cannot go beyond 1. So, that is this picture. Okay. So, also when we studied Taylor series, we sort of looked at this real function f of x equals 1 plus x squared, and I also gave this example to say it is not clear why in the real setting this function 1 by 1 plus x squared has a Taylor series expansion around 0, which has radius of convergence only 1. Okay. So, in the case of real numbers, it is not immediately clear why that happens. So, this the Taylor's expansion, by the way, is sigma n equals 0 through infinity minus 1 power n x power 2 n. Okay. And this is valid for modulus of x less than 1. Okay. So, the situation becomes clear when we graduate to complex function 1 by 1 plus z squared. So, let us consider the corresponding complex function 1 by 1 plus z squared, and it has a very similar Taylor series expansion. It is n equals 0 through infinity minus 1 power n z power 2 n around z equals 0, okay, and this is valid for modulus of z strictly less than 1. Okay. And in the case of complex functions, we know why the modulus has to be less than 1, because at z equals plus or minus I, this function has a singularity minus I or plus I, the denominator is 0. So, this function is undefined. So, you have a ball of radius maximum 1, okay, which is clear of these singularities of this function. Okay. And so, the Taylor series expansion stops at 1. Okay. So, the radius of convergence is 1. Earlier, we considered the function 1 by 1 minus z, which is equal to 0 through infinity z power n for modulus of z less than 1. All right, there is a pole at 1, and so this expansion has to stop there. Okay. But what we can do is, of course, it is analytic elsewhere. Okay. So, it is analytic everywhere out, other than at the point 1 on the complex plane. So, can we do something else to write 1 by 1 minus z as a certain series outside the disk of radius 1. Okay. Okay. So, in an open set which is outside the closed disk of radius 1. Okay. So, yes, we can do that by a small manipulation. We will write 1 by 1 minus z equals 1 by z or minus 1 by z times 1 by 1 minus 1 by z. Okay. And so, when modulus of z is greater than 1, okay, so outside the closed disk of radius 1, a modulus of z is greater than 1, and when this happens 1 by z has modulus strictly less than 1. So, we can expand this factor 1 by 1 minus 1 by z as a power series. Okay. So, what we can do is we can write that as minus 1 by z, okay, times sigma n equals 0 through infinity 1 by z power n. So, that is the geometric series, okay, and this is valid for modulus of z greater than 1. So, this is equal to minus sigma n equals 0 through infinity z power minus n, and then there is another factor, then that gives me a minus 1. Okay. So, I will rewrite this as sigma minus m goes from minus infinity to minus 1 z power m. Okay. By reindexing it, I can write this as m goes from minus infinity to minus 1. What that means is, I am allowing the index to start at minus 1 and go through negative integers until forever. Okay. So, but we know that this series converges, okay, and this is for modulus of z greater than 1. So, then we have expanded 1 by 1 minus z outside the disk of radius 1, closed disk of radius 1. Okay. And we will use this to do the following. We will consider this function, we will consider an example, okay, 3 by 1 minus z times 4 minus z. This function, okay, has two singularities, one is at 1 and another is at 4. So, there is a singularity at 1 and it has a singularity at 4. Okay. So, we just did something to expand 1 by 1 minus z outside the closed disk of radius 1. So, we have an expansion for 1 by 1 minus z outside of this disk, okay. And then we can do, we also know that, okay, we can expand 1 by 4 minus z, okay, inside so, I will do the hashing the other way, okay, inside a disk of radius 4 around 0. Okay. So, so we will see that we have an expansion of this function, okay, in an annular region between a disk of radius 1 and a disk of radius 4. Okay. So, let me first write this as partial fractions. We can write this as minus 1 by 1 minus z, okay, minus 1 by 4 minus z, or I apologize, this should be plus 1 by 1 minus z, and I can expand 1 by 1 minus z. Okay. So, when modulus of z is greater than 1, okay, I know that 1 by 1 minus z is equal to sigma, but from above, okay, minus of m equals minus infinity through minus 1 z power m, okay, and this series converges to 1 by 1 minus z when modulus of z is greater than 1. Okay. And likewise, when modulus of z is strictly less than 4, okay, this other part 1 by 4 minus z, okay, gives you 1 by 4 minus z can be written as 1 by 4 times 1 by 1 minus z by 4, okay, which is equal to 1 by 4 times sigma n equals 0 through infinity, okay, z by 4 power n. Okay. So, put together, these two expansions are valid on a common region, namely when when 1 less than modulus of z is strictly less than 4, we have this function 3 by 1 minus z times 4 minus z can be written as minus of sigma m equals minus infinity through minus 1 of z power m, okay, minus 1 by 4 times sigma n equals 0 through infinity z by 4 raised to n. Okay. So, you see that in the common region, okay, so the indices, one of the indices is running through the negative integers from minus 1 through ever, okay, and one of the indices is running in the positive direction through the non-negative integers n equals 0 through infinity. Okay. So, we have a sort of a series, okay, which is double ended. Okay. We are going to call this kind of series as double ended, okay, and each of them converges in the common region, okay, individually, and hence we say that when we put them together, okay, like this, they converge to this function on the annular region between 1 and 4. So, right, I mean 1 less than mod z less than 4 is an annular region. Okay. So, it is the region between a disk of radius 1, okay, and a disk of radius 4. Okay. So, it is all this region not including the boundaries. Okay. This motivates us to expand certain functions, okay, in annular regions, okay, and we will introduce what is called as Laurent series of functions in annular regions. Okay. So, first I will start with double ended series. Okay. We say sigma n equals minus infinity through infinity, a n converges, okay, if sigma n equals 0 through infinity a n and sigma n equals 1 through infinity of a minus n. Okay. What that means is the subscript of a runs through negative integers, okay, both converge. Okay. So, if both of them converge, we say that sigma n equals minus infinity through infinity a n converges. Okay. And in this case, we say what does it converge to? Well, n equals minus infinity through infinity, a n is equal to S 1 plus S 2, where okay, S 1 is n equals 0 through infinity a n, and S 2 is this other quantity n equals 1 through infinity a minus n, which we agreed already converge, which we supposed already converge. Okay. So, if we call the convergent quantities S 1 and S 2, then the original quantity n equals minus infinity through infinity is S 1 plus S 2. Okay. We say that is S 1 plus S 2. And with this convention, what we have is the Laurents theorem, which talks about expanding functions in an annular region as series, as a double ended series. Okay. So, we look at the annular region A equals z belongs to C, okay, such that R less than modulus of z minus A strictly less than S. Okay. So, let A be this annular region. Okay. What we will allow is we will allow R to equal 0, okay, but it is strictly less than S, okay, and S can be as large as it wants, it could be infinity. Okay. So, we will allow the radius R of the lower radius of this annular region to actually collapse to a point, okay, and then we will allow S to be as large as infinity. Okay. So, but here we have a strict inequality. Okay. So, here or here we have a strict inequality, and then and let f be analytic on A. So, f is a function, complex function which is analytic on A, then f of z can be written as sigma n equals minus infinity through infinity C n z minus a power n. So, you can expand f as a double ended series for z belonging to this annular region, where these coefficients are not alien. You can select coefficient C n to be 1 by 2 pi I integration around gamma of f of w by w minus a power n plus 1 dw, where that a is the center of that annulus, annular region, and where gamma, and where gamma is circle. So, its trace is a circle, is a positively oriented circle of radius r centered at A, and of course, the r lies between r and s. So, that gamma is contained in the annular region, and this is a. So, what that means is the trace of gamma is a circle, and gamma is oriented in the counterclockwise direction on that circle, and it travels once around that circle. So, that is your gamma, and when gamma is such, you can select these C n's to be 1 by 2 pi I of that integral. So, it is interesting, the coefficients look very similar to the coefficients of Taylor's theorem, except that you now have a double ended series when you have an annular region. So, that is Laurent's theorem. So, here is the proof of Laurent's theorem. What we will do is we will do the following by recomposing by a translation. We can assume that A is equal to 0. So, we are moving everything, we are moving all of this region to be centered, this annular region to be centered at 0. So, the function f sort of changes, but that is okay with us. So, we will assume that A is equal to 0, and if you want to modify it in another fashion, you can actually assume A equals 0 and work it out, and then transfer this series to a series centered at A, by classifying the functions to be of two types, series around 0 and series around A. Anyway, so you can do this and choose, let you will first fix, let z belongs to A. You will fix one point on the annulus, and choose P and Q, so that R strictly less than P is strictly less than modulus of Z is strictly less than Q is strictly less than S. So, I will show a picture is more helpful here. So, here is your annular region. Once again, R could be 0 and S could be infinity, but let us suppose that these are the coordinate axes, that is the annular region. So, this is radius R and that is of radius S, that is a circle of radius S, and the region in between is what you want, and gamma is a contour like that, oriented in the positive sense, that is gamma. Maybe we will use color. So, it is your gamma. So, Now, your choice of P and Q are such that I will not draw the coordinate axis, so that there is less clutter. Okay. So, here is your R, circle of radius R, here is a circle of radius P around origin. Okay. Here is a circle of radius Q, okay, and here is a circle of radius S. Okay. So, you have R, this is Q, sorry P, and that distance is Q, this P, okay, and finally that distance is S. Okay. And let gamma 1 and gamma 2, okay, be the simple closed curves whose trace is, okay, I will draw another picture, okay, is as shown, okay, whose trace and orientation is as shown. I need another picture. Okay. So, here is, now I will eliminate the curve of radius, sorry, the circles of radius R and S. Okay. So, here I am only going to draw circles of radius P and Q around the origin. Okay. So, here is your P, okay, and then here is your circle of radius Q. Okay. And your gamma 1, I will draw it in blue. Okay. It is the contour which starts here, you could assume, okay, or anywhere here. Okay. Firstly, Z is a point here, okay, and then it is any point. Okay. Notice your Z, the modulus of Z lies between P and Q. Okay. So, Z is inside here, okay, and so gamma 1 goes in this direction, okay, and travels in this direction, okay, and then goes around in the that direction, okay, halfway, and it goes this way, okay, and then it follows the half of the circle of radius Q. Okay, so, that is your gamma 1, okay, and gamma 2 is a contour which starts somewhere here, you can assume. Okay. So, it goes around on this circle of radius Q, okay, and it goes in the opposite direction on this. Okay. I am drawing it a little to the side because I do not want to clutter that line, but essentially it goes in the opposite direction along the same line, and it goes around in this direction around a circle of radius Q, okay, and it only covers half of this circle and goes back, okay, that way. So, it traces the same line once again, the same comment, okay, and it touches that point and then goes back like that. Okay. So, that is your contour gamma 2. Okay. So, that is the trace and orientation of the contour gamma 2. Okay. And now, the point is the integration along these line segments, okay, that you see here, which those line segments which pass through the annular region between P and Q, circles of radius P and Q, the integration along that cancels, okay, and then when you integrate along gamma 1 plus gamma 2, what is going to remain is only the integration along the outer circle and along the inner circle in the opposite direction. Okay. So, that is the idea. Okay. So, so f of z now, okay, is equal to 1 by 2 pi I times integration over gamma 1, okay, of f of w by w minus z dw, because gamma 1 okay, contains z in its interior okay, and f is analytic on and inside of gamma 1. Okay. So, since gamma f is analytic on and inside gamma 1 and z belongs to the interior of gamma 1. Okay. So, that is the trick. Okay. And also 1 by 2 pi I times integral over gamma 2 okay, f of w by w minus z dz. What is that? See dw, sorry, what is that? That is equal to 0, because z lies in the exterior of this curve gamma 2. Okay. Since f by f of w by w minus z is analytic for w belongs to inside of gamma 2 and w belongs to gamma 2 star. Okay. Whether okay, I should say f of w by w minus z is analytic on and inside inside the contour gamma 2. Okay. But when I say f of w by w minus z, there are two variables. So, I should exactly specify which variable I am talking about. So, I have okay, I have been clear. I am saying that with respect to w, okay, this function f of w by w minus z is analytic on and inside gamma 2. Okay. And so, this integration is equal to 0. Okay. And by combining these two things, what we can say is that f of z plus 0, okay, which is f of z, is equal to 1 by 2 pi I times integration over gamma 1, okay, gamma 1 f of w by w minus z dz plus integration over okay, I will rather take the minus of this. Okay. Okay, minus. So, f of z minus 0 technically okay, is minus integration over gamma 2 f of w by, oh sorry, I need a plus, I apologize, I need a plus, okay, f of w by w minus z dw, okay, need a plus. So, what that transfers to is 1 by 2 pi I integration over gamma 1 plus gamma 2 okay, f of w by w minus z dw. This is a dw etcetera. Okay. And gamma 1 plus gamma 2, like I explained, gamma 1 plus gamma 2 will give you integration on the circle of radius q okay, in the positive direction, and integration on the circle of radius p in the negatively negative direction. Okay. So, this is equal to 1 by 2 pi I integration on I will say C q, I will write what this is, okay, C q f of w by w minus z dw minus 1 by 2 pi I integration on C p f of w by w minus z dz. Okay. Here C p okay, is a okay, circle of radius p okay, okay, oriented positively short, and C q likewise is a circle of radius q oriented positively. Okay. And this is okay, they go around once, okay, only once on those circles, those are the contours, okay, and that is equal to 1 by 2 pi I first integration on C q okay, of sigma n equals 0 through infinity z power n by w power n plus 1 f of w dw okay, minus 1 by 2 pi I integration of on Cp of sigma m equals 0 through infinity of minus w power m by z power m plus 1 f of w dw. Okay, I am going to explain. So, what I am doing here is that I am taking 1 by w minus z, okay, and notice that z is in between the circles of radius q and p. Okay. So, what that means is that, or you can look at this inequality, sorry, you can look at this inequality, modulus of z is in between p and q. Okay. So, w when it ranges on C q, okay, the modulus of so on is equal to sigma z by 1 by w times z by w power n equals 0 through infinity, okay, on C q. Okay. So, the modulus of z by w is strictly less than 1 when w is on C q. So, 1 by w minus z can be expanded as geometric series by pulling out 1 by w, okay, and you have 1 by 1 minus z by w, which you can expand as geometric series. Okay. And likewise, for the second term, what I am using is when you have w on C p, okay, w by z is going to be less than 1 in modulus. Okay. W by z can then be used, you can use geometric series to expand 1 by w minus z. You can do the trick that we did at the beginning of this session, okay, for 1 by 1 minus z. What you can do is you can pull out a 1 by z, okay, times 1 by w by z time minus 1, okay, and that can be expanded as geometric series. So, you get 1 by z times minus of sigma and m equals 0 through infinity of 1 of w by z power m, okay, and hence the second expression as a series. Okay. This is, I should say, on C p, because the modulus p is strictly less than the modulus of z. Okay. You can do this for w belongs to C p. So, that is that is how we introduce these series into the integrands, okay. And now, we want a lemma which exchanges the order of summation and integration. Okay. So, that we will recall a certain lemma we proved before Taylor's theorem. Okay. So, it is an exercise for the viewer, it is an easy exercise to show that the order of integration and summation can be exchanged. Okay. So, please try that, and when you do that exercise, this is going to be equal to sigma n equals 0 through infinity, okay, integration over C q of f of w by w power n plus 1 dw, okay, times z power n, okay, and maybe I want to put the 2 pi I inside as well. Okay. So, I will write n equals 0 through infinity, sigma n equals 0 through infinity 1 by 2 pi I, okay, and then plus sigma m equals 0 through infinity 1 by 2 pi I times integration over C p of w power m f of w dw, and then there is a 1 by z power m plus 1, 1 by z power. So, I will write simply divide by z power m plus 1. Okay. And so, now by a certain version of Cauchy's theorem. Okay. Integration over C q can be replaced by integration over gamma. Okay. So, now by Cauchy's theorem, okay, so integration f of z is equal to. So, this is all equal to f of z. So, this f of z is equal to n equals 0 through infinity 1 by 2 pi I integration over gamma. So, I am replacing C q with gamma, okay, f of w by w power n plus 1 d w, okay, plus integration from n equals minus 1 through minus infinity, okay, or minus infinity through minus 1, whichever way, 1 by 2 pi I integration over gamma of f of w d w. Okay, f of w, I will say z power m divided by w power n plus 1 d w. Okay, I am missing z power n here, I apologize. I should have a z power n here, and this is z power n. Okay. So, putting these together, okay, so I have changed the index here. I have converted m to n, okay, substituting n equals minus m minus 1. So, I am taking n equals minus m minus 1. Okay. So, putting these together, we have what we want. This is equal to sigma n equals minus infinity through infinity. So, firstly both of these converge, of course, okay, and then this is equal to n equals minus infinity through infinity of 1 by 2 pi I integration over gamma of f of w times z power n by w power n plus 1. Both these now look the same, okay, d w. Okay. So, your C n is indeed 1 by 2 pi I times integration over gamma of f of w by w power n plus 1. Okay. So, that completes the proof of the Laurents theorem. Okay. So, we can expand f of z as series in an annular region where f is analytic. The important step that we did not, we left it as an exercise to the viewer, is the step here, okay, that the series and the summation, order of summation and the integration can be exchanged. Okay. So, please complete that exercise, and when you complete that exercise, you have the proof of this theorem. Okay. Now, what we are going to do is we are also going to show that this series expansion is unique. Okay. So, uniqueness of Laurents expansion. Okay. Let f be analytic, okay, in A equals z belongs to C, the same setup, R strictly less than mod z minus A strictly less than S. You will allow R to be 0 and you will also allow S to be infinity. Okay. And suppose that f of z is equal to sigma n equals minus infinity through infinity d n z minus a power n. So, suppose you are able to expand f of z as a double ended series in some other format, okay, with other coefficients d n, z belongs to a, okay, then it has to be that d n is equal to C n coming from above, okay, for all n belongs to z. Okay. I can directly say this as the d n is equal to 1 by 2 pi I integral gamma f of w by w minus a raised to n plus 1, okay, d w. Okay. So, what that is saying is that if you are able to expand f as a double ended series, then the coefficients have to be of the form that Laurents theorem specifies. Okay. Okay. And the proof is as follows. Once again, you can assume that A is equal to 0. Okay. Choose R such that R lies between capital R and capital S. Okay. Then 2 pi I times C n, the nth coefficient, okay, from the theorem. Okay. So, this C n coming from previous theorem, okay, is equal to integration over C r, okay, f of w by w minus a power n plus 1 d w, that is the coefficient here. Okay. So, and then that is equal to integration over C r. C r is a circle of radius r here, once again oriented in the positive sense. Okay. So, I am not writing that here. This is equal to sigma r equals minus infinity through infinity of d n w minus a. Okay. So, this is r k equals minus infinity through infinity of d n w minus a power k, because I can write f like that, okay, and then times 1 by w minus a power n plus 1. Okay. So, f we assume can be written as d n times z minus a power n, okay, for z belongs to a, and here the w belongs to is on the contour C r, which means it belongs to a. So, you can write f of w in that fashion, okay, and then that is equal to integral over C r sigma k equals minus infinity through infinity of d n times w minus a power k minus n minus 1. Okay. So, I cancel the factors of w minus a to get that. Okay. Okay. Or I just change the exponent. Okay. So, this is equal to integration over C r sigma k equals 0 through infinity d n w minus a power k minus n minus 1 d w plus integral over C r sigma m equals 1 through infinity d minus m. So, I am splitting the integral, okay, on two series w minus a power minus m minus n minus 1, okay, dw. Okay. And then this is 2 pi I times C n now is equal to, once again I will invoke that theorem which exchanges the order of summation and integration. Okay. So, that gives me k equals minus infinity through infinity, okay, of dk times integration over C r of w, okay, w minus a power k minus n minus 1. Okay. So, I actually never used the fact that I can assume that a is equal to 0. Okay. So, I actually can eliminate that. I have been doing this around a itself. Okay. So, this boils down to the fundamental integral, and we know that this integral. So, I am summing these two things, putting these two things together, okay, and we know that the fundamental integral is 0 except when the exponent is minus 1. Okay. So, this gives us 2 pi I, this summation, all the terms in the summation are 0 except when this exponent k minus n minus 1 is equal to minus 1. Okay. So, which means this is when k equals n. So, you are left with just d n, okay, sorry, 2 pi I times d n. Okay. So, that tells you that the C n, which is coming from the previous theorem, which is 1 by 2 pi I, all that integral over gamma f of w by w power n, okay, w minus a power n, okay, n plus 1 d w, okay, that is your C n is equal to d n. Okay. So, that proves the uniqueness part of Laurent's expansion. Okay. So, there is a unique expansion as a double ended series of f where the coefficients are of this form or of this form, which is 1 by 2 pi I times integration over gamma of f of w by w minus a power n plus 1 dw. Okay. So, I will stop here.